Hello learners, welcome to this course on embedded system design using AT89C51 microcontroller. In this tutorial, I will be discussing about on how to interface an 8-bit ADC0808 IC with the microcontroller. So ADC0808 IC is an analog to digital converter. So it converts your analog input to a 8-bit digital value. So an important aspect of any embedded system is to sense the parameter from the environment. After sensing the parameter from the environment, we need to do some modification to the environment through the actuators. So the first initial step is we need to sense the parameters. To sense the parameters, most of the sensors are analog in nature. But our microcontroller will work with the digital data. So in order to provide this sensor data to a microcontroller, we need to have an IC which can convert this analog value to a digital value. So one such IC is your ADC0808 IC, which is a 8-bit analog to digital converter, where this 8-bit represents after the conversion process our obtained digital value will be of 8 bits. Similarly, we have 10-bit ADC, 12-bit ADC, generally we call it as a n-bit ADC, which means after the conversion process we get a n-bit result. The ADCs can be of different types. So in ADC0808, it is fabricated using your successive approximation ADC. In successive approximation ADC, we will be having a sample and hold circuit. So the sensor data is given as an input to your sample and hold circuit, and the samples are selected and the sample voltage comes as an input to your comparator. Then we have a successive approximation register which holds the combination of binary bit patterns. Since it is an 8-bit ADC, we will have a combination from 8 zeros to 8 ones. 8 zeros to 8 ones. So initially this 8 0 will go to your digital to analog converter, which will convert your digital value to an analog voltage. So 8 zeros comes as an input to your DAC, it will produce an voltage. And this voltage is compared with the input sensor sample voltage. If it matches, then that 8 zeros is the corresponding output for the input voltage. If it does not match, then the next binary bit pattern 701 will be taken from the SIR and it is given as an input to your DAC, and the DAC will produce the corresponding voltage to that binary bit pattern. Again, this voltage will be compared with your sensor input. If it matches, then that result 701 will be coming as an output. If it does not match, then it goes to the next combination. So like that, each input in a SIR is converted into an analog voltage using a digital to analog converter, and that voltage will be compared with your input sensor voltage. Once a match occurs, then we know the binary bit pattern. That bit pattern will come from your SIR register as an output as D0 to D7. So in order for this ADC to work, we need to provide an reference voltage. So either I can give the IC supply voltage as a reference voltage, or we can use some external reference voltage, or it can also be internally generated. So one of the key aspect of your A to D converter is resolution. So resolution is nothing but the smallest voltage change represented as a proper digital output pattern. So if I want to calculate a resolution, for example, let us take an 8-bit ADC. So N equal to 8-bit. And I am going to take a reference voltage of 5 volt, which is nothing but your 5000 millivolt. So the resolution is computed using this formula, V reference divided by 2 power n minus 1, which is nothing but 5000 millivolt divided by 2 power 8 minus 1, which turns out to be 19.6 millivolt. So what does this mean? Each step is going to have a voltage variation of 19.6 millivolt. So for example, my low level, which is your input voltage, is 0. If my input voltage is 0 volt, then the corresponding binary bit pattern generated from our ADC is 8 zeros. The next step, the next measurable voltage is 19.6 millivolt. That is the resolution of your ADC. For the next measurable voltage, the binary bit pattern is 7 zeros 1. Then again I have to add 19.6 millivolt, it becomes 39.2 millivolt. So for 39.2 millivolt, the binary bit pattern obtained is 6 zeros 1 0. Same way like that it goes on till your final reference voltage 5000 millivolts. So if my input voltage is 5000 millivolt, then I will get 8 ones as an output. So we have about 256 quantization steps from 0 to 255. So each step has a voltage variation of about 19.6 millivolt. So if my sensor gives a voltage less than 19.6 millivolt, then we cannot resolve it properly. We cannot obtain the proper digital binary bit pattern. In that case, how to get a smaller resolution or a higher resolution? We can adjust the reference voltage. Instead of using a 5 volt as a reference voltage, we can use 2.5 volt as a reference voltage. In that case, my each step will have a variation of about 9.8 millivolts. So you can see the variation. Even a smaller voltage change can be represented in a proper binary bit pattern. Another option is, instead of using n equal to 8, I can use n equal to 10. In that case also, we can increase the resolution of your ADC. So resolution is one of the key parameters of your ADC, which represents how small and voltage can be represented in a proper binary bit pattern. The main applications of this sensor, we can use it in temperature based home automation, industrial process automation. Now let us look at a simple simulation where we are going to use an ADC0808 IC, which is a 28-pin IC, and I am going to connect a sensor. So sensor here I am going to consider it as a potentiometer. I am going to consider it as a potentiometer, variable resistance. So by varying this potentiometer, the voltage given to this input can be varied. So this ADC0808 IC, it can support up to 8 sensor data, so which is represented by IN0 to IN7. So 8 sensor data can be connected. We are going to connect one potentiometer to IN0. Then the corresponding digital bit pattern output will come from your out1 to out8, where this out1 represents the MSB bit and out8 represents the LSB bit. Then we have the address lines, address A, address B and address C. So these 3 lines are used for selecting the corresponding input. So if I want to select IN0, then I have to give 0, 0, 0, which will select IN0. If I give 0, 0, 1, then it will select IN1. 0, 1, 0, IN2. 1, 1, 1, it will select IN7. So this add A, add B, add C. So these 3 lines are used for selecting an input signal. So in order to latch this address, address A, address B and address C, we will use this ALE. ALE stands for address latch enabled. So if I give a logic 1, this address will be latched and the corresponding input will be selected. And the reference voltage can be given through this V reference plus and V reference minus. So for this example, we are going to use the IC supply voltage as a reference voltage. So we connect it as it is. Then in order for the conversion process to happen, we need to provide a clock source to this ADC. So up to 1.2 megahertz clock can be connected to your ADC. So for this example, I am going to connect a clock of about 500 kilohertz. So 500 kilohertz clock frequency is connected to the clock line. Then we have 3 more lines. One is start. So start the conversion process to give an indication that you start the conversion process. Once the conversion is complete, the output is produced. That will be indicated by the end of conversion signal. So start the conversion process should be given from the programmer. Once the conversion is complete, the ADC will give an indication through end of conversion process. Once the conversion is complete, we need to get the output through this out1 to out8. In order for getting the output from out1 to out8, we have to set the output enable pin to go to high. If output enable pin is high, we will get the output through this out1 to out8. Then I am going to connect a bar graph LED to this out1 to out8, thereby we can visualize the result. So here we set an analog voltage through a potentiometer. Then we close this switch so that the conversion process will happen. So conversion starts. So the analog value is converted into a digital value. So after some time we try to release this. So thereby we stop the conversion process. Once the conversion process is stopped, if the process is complete, end of conversion signal will be highlighted. Once end of conversion is highlighted, output enable will be given and we will get the output here. So here if you see the output, it represents 1, 0, 1, 4 zeros, 1. That is the output coming from your ADC after the conversion process for an input voltage of 3.14998 volt. We get this output. So if I see the output, so 1 0 1 4 zeros 1, which turns out to be 161. So how to calculate the voltage from this binary bit pattern? So we can convert this ADC value into the resolution of your ADC will give the measured voltage. So what is the ADC value? ADC value is 161. So we know the resolution of our ADC. If my reference voltage is 5 volt and it is a 8-bit ADC, we know the resolution is 19.6 millivolt. So we multiply this 161 with 19.6 millivolt, which turns out to be 3.15 volt. So that is what we measure using the voltage probe in our circuit. If my binary bit pattern, output binary bit pattern is 8 ones, which turns out to be 255. In that case, what will happen? 255 into 19.6 millivolt, which turns out to be 5 volt. So like this, by looking at the output binary bit pattern, we can estimate what is my input voltage to the ADC. Now let us visualize the simulation part. So here I show a typical circuit developed in Proteus 8 environment, where I have an ADC0808 IC and we have connected a potentiometer to the IN0 pin of your ADC0808 IC, and this input is selected through the address lines A, B, C, and it is connected to ground, which means 0, 0, 0. So IN0 will be selected. In order to latch the information, we give ALE to be 1, and the reference voltage is given as a supply voltage. Then we have a clock source which is connected with the 500 kHz. Start the conversion process. So when I close the switch, conversion will start. When I release the switch, conversion will stop. Once the conversion stops, the end of conversion bit will be highlighted and we will get the output through this out1 to out8, and it is connected to a LED. So where this first LED on top will give the MSB bit, and the 8th LED in the bar graph LED will give the LSB bit. So if I run this simulation, right now you see nothing happens. So we will set some voltage, so I can vary this potentiometer value. So let me keep it as some voltage like 2.5 volt. Okay, so 2.5 volt, right now I have kept it. Then I am going to start the conversion process by pressing the switch. So conversion starts. So after some time I release it. You can see end of conversion is highlighted. So end of conversion is connected to the 10th LED. So once the end of conversion is there, we get an output here. So it represents 0, 7 ones, 0, 7 ones is the binary bit pattern. If I change the voltage, let me change it to some other voltage. So 30% of the reference, 35% of the reference voltage. Then again when I close it, start the conversion process. After some time, let me release it. You can see the converted result. So now the output is 0, 1, 0, 1, 1, 0, 0, 1. So that is the output coming from your A to D converter. So from this binary bit pattern, we can multiply this value with the ADC resolution to get the input voltage, which is 1.75. So now let us look at how to interface a microcontroller with the ADC0808 IC. So here what I am going to do is, I am going to take AT89C51 microcontroller. We are going to connect a ADC0808 IC, and the input is connected through your potentiometer to IN0 pin, and the output which we get from the ADC is connected to port 1 of your AT89C51 microcontroller. So we are going to read the data through port 1 and send the data through port 3. So we are going to read the data from port 1 and send the data through port 3 to the LEDs. So we are going to use just a microcontroller here to read the data from ADC and send that value to a bar graph LED through port 3. And other control lines like address A, address B, address C, ALE, start the conversion process, end of conversion process is connected to the port 2 of your microcontroller. So now let us see the simulation part. So here we have a typical circuit connected in Proteus 8 environment. So here you see the AT89C51 microcontroller is connected with the oscillator circuit. So we are going to use an oscillator frequency of 10 MHz connected to XTAL1 and XTAL2, and there will also be a reset circuit. Then we connect a ADC0808 IC. So here I connect a potentiometer to IN0, and the address lines, address A, address B and address C is connected to port 2.0, 2.1, 2.2, and ALE is connected to port 2.3. Then we have two more control lines, which is your SOC, start the conversion process, and end of conversion process. So start the conversion process is connected to port 2.6, end of conversion process is connected to 2.7. So if you see here, this 2.0, 2.1, 2.2, 2.3 all are outputs from your microcontroller. Address A, address B, address C, and ALE is the output from your microcontroller. Same way, start the conversion process also is the output from your microcontroller. Whereas end of conversion is the input obtained from your ADC. So 2.7 I need to configure it as an input. Other pins in your port 2 can be configured as an output. Then we connect a reference voltage of 5 volt to the V reference plus and V reference minus, and the output enable bit is connected to your supply. So that the output is enabled, we will get the output from your ADC. And we are going to use a clock source of 500 kilohertz connected to your clock line, and the output from out 1 to out 8 is connected to port 1, 1.7 to 1.0. So we read the data from your ADC through port 1 and send the data to your port 3. Port 3 is connected to your bar graph LED. So here this port 3.7 is your MSB bit and port 3.0 will be your LSB bit. Now let us look at the programming part. So we will be building the program using your Micro C 4 Pro for PIC for 8051. So here we take a main program. First thing is we need to configure our ports as an input port and an output port. So port 1 we are going to use it as an input port. How to declare it as an input port? We have to set a value of 1 to the port pins. Since all the 8 port pins we are going to use it as an input, we specify port 1 as 0xFF. Port 3 we are going to connect a LED, so which is configured as an output by setting each port pin to be 0. So 0 means the port pin will be configured as output, 1 means port pin will be configured as input. So port 3 is assigned with 0x00. Then port 2.F0 is connected to your address A, which is again an output line, so it is set with 0. Same way address B is also an output, address C is also an output from your microcontroller. ALE signal, which is connected to port 2.F3, is also configured as an output pin. F6, sixth pin, which is nothing but to start the conversion process, is also an output from your microcontroller, whereas the last 2.7 is your input pin, because it is connected to the end of conversion process. Once the process is completed, the end of conversion will intimate the microcontroller that process is complete, you can read the data. That will be indicated by 1 to configure it as an input pin. So after all the port configuration is over, we set the address for your address A, address B, address C. So address A, address B, address C, we set it to be 0, 0, 0. Then I set the ALE to be 1 so that this address can be latched by your ADC. Once the address is latched, input 0 will be selected. So then in a while loop, I am going to start the conversion process by putting port 2.F6 to be 1. So we wait for some time, then we stop the process. Port 2.F6 equal to 0, which will stop the conversion process. So again we wait for some 1 second, then we check whether end of conversion is obtained. So if end of conversion is obtained, we will get port 2.F7 equal to 1. In that case, what we do, we read the value from port 1, send it to port 3. Just very simple. We start the conversion process, after some time we stop the process, then we check whether end of conversion is obtained. If end of conversion is obtained, we read the data from port 1, send it to port 3. So this is a simple program to read the data from your ADC through port 1 and send it to port 3. So once we have written the program, we can compile it so that the embedded C program can be converted into hexadecimal file. So in order to do that, we use this build option so that it gets converted into hexadecimal file. Then we go to the Proteus environment, right click on the IC, edit properties. So the oscillator frequency which we are going to use is 10 MHz, and select the program file, which is nothing but your ADC_MCU_LED. So this is the hexadecimal file which we have created. So this we try to import into our IC. So after importing our hexadecimal file to the IC, we need to run the simulation. When I start executing this, you can see right now for this input voltage, 80% of the reference voltage, we get this binary bit pattern. So the binary bit pattern is 11001100. So if I change this voltage, okay, so if I change it to some 50% or 60%, so right now it is 53% of your reference voltage. You can see the corresponding binary bit pattern here, 1 4 zeros 1 1 1. So again if I change the input voltage, you can see a variation. Okay, now it is changed to 0 1 0 0 0 1 1 1. So thereby we can read the sensor data. You can read the sensor data through a microcontroller, and the value can be displayed in your LED, bar graph LED. So in this tutorial, I have discussed about on how to get a data from ADC0808 IC and how it can be interfaced with your AT89C51 microcontroller, and how to display the ADC output in LED. So this is a typical circuit which I have shown. So here you can see the output voltage is 11001100. So this is the corresponding program which I have explained you just now. Thanks for watching. Please subscribe for more technical learning. Thank you.